Hello, everybody. So we're going to continue with our discussion on um, hypothesis tests. So I've put a little summary up on one side here. This is the part of the tests that are similar for everything, right? So we talked last time about these pieces. I'm mostly going to talk through these by using examples, but we choose our null and our alternative hypothesis. H naught is the null hypothesis. HA is the alternative hypothesis. H naught is the thing that we assume to be true. It's the idea that there's no effect to whatever we're testing, or that the population we're looking at is the same as everybody else. Whatever it is, we're trying to test for some kind of difference, that a medicine works or something like that. H naught is that there is no effect. It's the thing we're not interested in. We're usually interested in the alternative hypothesis. We're often trying to prove that claim. And then here's where the big differences come in. We determine the distribution we're going to use. And we have the same three situations that we had for confidence levels. In this case, it's instead of finding a confidence level for, it's testing for. So we might do a test on the population mean when we know the standard deviation, population mean when we don't know it, and a population proportion, right? So we determine that statistic as well as the level of significance that we call alpha, which will usually be given. Let's see. Then we compute the test statistic. And so that, if you look on the left of the screen here, is what these three columns are about. Depending on which of those three types I just talked about, we have the mean and a standard deviation is known. We have one test statistic. The mean and the standard deviation is unknown. We have another test statistic. And then the proportion, we have this test statistic. So we will be using these for the following three tests. And then once we compute this test statistic, we then compare it to alpha. There's a couple different ways to do that. I'll do both ways over the course of these examples. We either compute the test statistic and compute the probability of that test statistic happening given the null hypothesis is true, or we just compare the test statistic to the critical values that are also related to to alpha, the level of significance. So I know there's a lot of moving parts, but I'm hoping that we'll quickly see that we repeat a lot of the same kinds of steps over and over again, and so we probably will begin to get pretty familiar with them quickly. So let's go ahead and do an example. So our first one is about a study into blood glucose levels. For obese patients, they're known to have a mean of 112 milligrams per deciliter with a standard deviation of 11. And there's a researcher who believes that people in a particular region will have different levels because of a variety of characteristics of the community, right? So maybe there's a community that has a significantly different relationship with diet, maybe air quality, maybe there's a combination of things that she believes will change these glucose levels, right? And so she conducts the study with 40 patients and finds that the mean glucose level is 116 milligrams per deciliter, and we're going to test with a 5% level of significance. So let's see, we want to choose H naught and HA. So H naught is that there's nothing different about these people, right? That's not what we're testing. We're testing her claim that there is something different. So H naught is that there's nothing. In other words, the mean among these people is still just 112. Okay, no difference than the general population. The alternative hypothesis is that the mean, now notice, the researcher isn't making a claim whether it's bigger or smaller. The mean is, or the claim is simply that because of all the characteristics of the community, the mean will be different. So this is a mean of, this is that the mean does not equal 112, okay? So there's our null hypothesis. Let's think about the distribution. We have the mean of a population, so we're testing the mean, and we know the population standard deviation, right? We're assuming this stuff to be true for the test. So we're in this first situation. And what that means is our test statistic is going to be Z equals the sample mean minus the population mean divided by the standard deviation that has been divided by the square root of the sample size, okay? So in this case, our sample mean is 116, our population mean is 112, our standard deviation is 11, and we're dividing by the square root of 40. I computed this and I got 2.300. Oh, I forgot one more thing. I should have said in this first step, the level of significance, it's given here. Alpha is 5% or 0.05, okay? So now we want to know what to conclude based on this test statistic. So I'm gonna do this one in the following way. I'm gonna look at critical Z values. All right, so let me draw a picture to illustrate this point. So this is the picture of our standard normal distribution. What I want to do is find critical values with the following properties. Between these two values, we have 0.95 area, which means outside of them, we have 0.05 in total, which means each of these tails has 0.025, right? The reason I'm doing this test this way with two tails, looking in both directions, this is different than the type I did yesterday, is because of what we have here. The researcher wasn't trying to prove that the mean was higher or lower, just different. And so the test is set up to say, we want to know if different can mean bigger or lower, so we're looking in both directions when we test this way, right? And so we split that alpha up into these two tails, right? Well, it's simple enough to look up in an inverse normal calculator. In fact, you'll probably remember these values from doing 95% confidence intervals, right? Notice in the middle is our 95% data that we use to determine the critical Z-scores for those confidence intervals. And so all we have to do to check now is our Z-score inside or outside of these tails. In other words, in these tails, in either tail, is what we might call the zone of rejection. So remember, we're testing to see if what we just got, this sample with 116 milligrams per deciliter, if that's a rare enough event to believe there's something more here going on than random chance. More rare is further away from the mean. So we're testing if our test statistic is further away from the mean than these critical values. And in fact, it is, right? Our test score is 2.3. That's going to be somewhere up here, which means we will reject H naught with a 5% level of significance. Right? The idea being, again, this is under the assumption that H naught is true. That would imply that what we just did, getting 40 patients with this higher blood glucose level, that was just an extremely rare event. We think it's more likely that actually this community has a different mean glucose levels. Okay, and that's the totality of the test, right? That's right. Yesterday, or in the previous video I did one, there was a whole bunch of stuff about the central limit theorem. That stuff is still true, but we don't need to do it each time. We can focus on these set of steps. Okay, let's do another example. Actually, let's do these in 3 separate videos. So I'll stop this one here, and I'll have another video with the next example soon to follow. Okay, see you next time.